Okay, in this video I'm going to describe some set theory basics, and here we're going to get just enough set theory so that we can use it to help us move forward this semester with some other topics. The basic idea of a set is that it is a collection of objects of some sort, and I'll illustrate this by example. So for example, I'm going to define the set A. We use capital letters to denote sets, and the set A in our case here, we can specify a set by simply listing the elements of that set. That is, the objects which are in that collection. Okay. What we do is we use curly brackets, and we simply list the elements in the set. This is the easiest way of specifying a set. So we've define the set capital A. We normally use capital A, B, C, D, maybe S, T, U, and V for sets. And so, for example, we can talk about what the elements of this set are by making statements like this. Little a is an element or is a member of the set A. Okay, so is an element of. So we say little a is an element of the set big A. Okay. Similarly, little d is not an element of the set big A because little d is not in that set. Okay. We can also talk about the size of a set, and the notation we use for that is absolute value signs. So it looks like the absolute value of a number, but it's called the order of the set. And in this case, the order of the set A is 3 because it contains 3 elements. Okay. A couple other facts about sets are, number one, that no elements are repeated, no repeated elements. And the other fact is that there is no order in a set. Now we're going to see later on the semester that we can impose an order on a set. We can say, suppose we have the set A with an imposed alphabetical order, and we can do that. But this set A, B, C, even though it looks like they're in order, there is no intrinsic order in the elements of a set. Okay. Another thing we need to do is to consider the notion of set equality. So for example, if I define, here I'm going to write 2 sets, but I'm not going to assign capital letters to them, but that's okay, I'm allowed to do that. I can make a set that has the elements 2, 3, and 1 in it, the numbers, and I can say that that set is equal to the set 1, 2, 3. So this is set equality. 2 sets are equal when they have exactly the same members. Okay, and we just use an equal sign there. And you can see that this little, this demonstrates that order doesn't matter. Similarly, if I were to define a set with a triangle, a circle, and a square in it, I would say that that set is equal to the set where, for some reason, I put 2 copies of the triangle. Okay, so repeats don't count, essentially. Okay, and so this set equality here, not only are they in different order, but if you happen to, for some reason, repeat an element, it simply doesn't count. Okay. A very useful way of specifying sets is called set builder notation. And I'll show you how this works here. Suppose I define the set B to be the numbers 1, 2, 3, and 4. Okay. I could just as easily, and perhaps more easily in many cases, define this set as follows, using what's called set builder notation. I could say it is the set of all x's such that x is an integer and 0 is less than x is less than 5. And then I add my parentheses there. So what we do is we say it's the set of all objects such that, and then we have some sort of a condition over here, and we might have multiple conditions. You know, for example, I said I made it so that there were 2 conditions, and both of these conditions have to be met. And you'll notice I use strictly less than here on both of these, and that means 0 and 5 are not members of this set, because that otherwise I would have to write less than or equal to. So 0 and 5 aren't, but 1, 2, 3, and 4, because they're all integers between 0 and 5. Okay? And this is a very common way of specifying sets. So for example, here I'll give you a few very common sets that we often use, sets of numbers. So for example, Z is the set of integers. Let's see. I can't back up, but I can erase. Okay, hold on here. I'm going to write Z equals the set of integers. One way to specify that would be to list elements. And this is going to be an illustration of the dot, dot, dot notation, where we can use dot, dot, dot after we've established a pattern. So I'm supposed to have 3 dots at the end here also. So dot, 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 -1, 0, 1, 2, dot, dot, dot. That's the set of integers. The set of natural numbers is non-negative integers, 1, 2, 3, dot, dot, dot. Okay. And we can write the naturals as the set of all x's that are integers, the set of all x that are an element of the set of integers, or we could just say the set of all integers such that x is strictly greater than 0. And that's the natural numbers. And this is natural numbers. Okay, so there's a basic introduction to the basics of sets, set builder notation, and a couple of sets that will be useful to us. And this also illustrates a different usage, or another example of set builder notation. This is very common to actually say the set of all x that satisfies some conditions such that even more conditions are satisfied. Okay.